In this video, we're going to look at an example of finding the volume of a solid by expressing it in cylindrical coordinates and using a triple integral. So we've got the solid. It lies in between the paraboloid z equals x squared plus y squared and the sphere x squared plus y squared plus z squared equals 2. The first thing we're going to do is figure out where these two surfaces intersect. So if we replace the x squared plus y squared in the sphere equation with z, we get z plus z squared equals 2. Bring the 2 over and factor and get the z has to be either negative 2 or 1. Of course, z can't be negative 2 because z equals x squared plus y squared is non-negative. So we must have z equal to 1, or x squared plus y squared equals 1 is the intersection of the two surfaces. So what that means for us is that this solid lies over the region x squared plus y squared equals 1. So we can rewrite that region that it lies over in terms of polar coordinates. If it's over the region x squared plus y squared equals 1, then we can describe that as r goes from 0 to 1, and the theta goes from 0 to 2 pi. If we look at this equation here, if we have the x squared plus y, z equals x squared plus y squared, over here, notice that this piece is going to be actually smaller for a while than this piece here. So we're looking between the x squared plus y squared as our lower bound for our surface and the x squared plus y squared plus z squared as our upper bound. If we solve for z, we know that this is above the xy plane, so we're going to use the positive square root. We move the x squared plus y squared over and take the square root, we'll get z equals the square root of 2 minus the quantity x squared plus y squared. But again, we can rewrite x squared plus y squared as r squared. So our z bounds go from r squared to root 2 minus r squared. So now we're ready to do the triple integral. To find the volume using a triple integral, we just need to integrate dv over the solid. So we replace the differential with r, dz, dr, d theta when we convert to cylindrical. The z's are going from r squared to root 2 minus r squared. The r's go from 0 to 1, and the thetas go from 0 to 2 pi. Notice that there aren't any thetas in here, so I can pop the theta piece out. Take that integral, I just get 2 pi. For the second piece, I want to integrate with respect to z first, so I just get rz. When we plug in our endpoints, we'll get r times root 2 minus r squared, and then minus r cubed. That first piece, we need to do a u substitution. If we do that, we should get an antiderivative of a negative 1/3 times 2 minus r squared raised to the 3/2 minus a 1/4 r to the 4th for the second term. Plug in our endpoints and simplify. We should get pi over 6 times the quantity 8 root 2 minus 7.